John Burns is an assistant professor of marine sciences at Hilo, so we're really happy he was able to make the long journey over here for the day. He has a PhD in biology from right here at in Manoa and has been studying coral reef ecosystems for the past 10 years. His recent work is focused on developing new techniques for three-dimensional mapping of coral habitats using innovative science tools. His talk is entitled A Comparison of the Diagnostic Accuracy of In-situ and Digital Image-Based Assessments of Coral Reef Health and Disease.
Thank you. I cheated and made a new title that I found to be far more compelling. Human versus machine.
New Terminator movie and all that.
Yeah, uh-oh. Let's see if at the technology conference I can harness the technology. Human works with machine, start slide. So, I started to phrase it this way with humans versus machines because I think that's where our brains sort of go when we think about machine learning and AI and it's funny because we've been building machines to help our work since the beginning of human existence. Really, all of the work that we do is aided by these machines in one way or another. But now more than ever, we have this hot debate as to what's better. Is the human observer or can AI or machine learning complement or outcompete that? We all know the fable of John Henry versus the railroad. We love to pit humans against computers to play chess. I don't know why that's so exciting. Everyone remembers Neo versus the Matrix, another epic battle. But in the realm that I work at, I strangely think it's more similar to what happens right now at factories at Amazon. So I lied a little bit. It's not really anything I do human versus machine. It's human with machine and how we make that work. So for example, here in all the factories now, instead of it being human jobs and machine jobs, they task them together and try have robots do what can be done to enhance the efficiency of the human work. And so it's finding that connection where both are complementary. And where I try to apply that and what I'm speaking about today is coral health and disease. So I've been studying coral diseases throughout Hawaii for a significant period of time, primarily because we keep seeing increases in these diseases, yet we have a very poor understanding of what is exactly causing them, driving them, and we do know they have a very detrimental impact on ecosystem function. So we're very curious to understand it better. So I spent years working on developing ways to use structure from motion photogrammetry underwater, and primarily it's been used to characterize these reefs. So with a 3D model in the talk that you just saw, it gives us a much better perspective, a permanent baseline, a way to go to beyond just a simple 2D image. But with coral health surveys, we haven't really embraced it 100% yet. Now, conventional methods are great because our expert eyes are there. We're literally on the reef. We can look around the coral, we can spend as much time as we need, but as anyone in here who dives knows, we're limited. There's constraints, air, time, depth, etc., so it can be difficult. Whereas using digital methods, especially 3D, we bring our data set back. We have it as long as we can preserve it, and at that point we can have repeated observers look at the same imagery. We can look at it at scales that are very large down to scales that are very small. It's high resolution, but it does come with a computation cost. It's not easy. Nothing's free. So I want to share with you today a short study we did over the summer. It was actually REU based, and what we wanted to do was actually assess performance. So we did in situ conventional observations of coral health, and then simultaneously created digital mosaics and 3D models, and then analyzed those same plots for the same characteristics of coral disease. So what we were doing was using a latent class model to see how the sensitivity and specificity of these two methods differed. Simple question, what's better at detecting coral disease? Then secondly, build up some hierarchical models and look at the performance among all these conditions. So in another simple manner, using these two diagnostics, which is better among all these conditions specifically. So we went out, and for this we tried to keep it simple. So we had divers use just 1x1 quadrats, and then we used NOAA training materials, did conventional NOAA coral health survey, looked at every colony in that plot, and then immediately used structure from motion photogrammetry techniques to capture imagery and then reconstruct it into what you're seeing here as a two-dimensional mosaic as well as a three-dimensional model. Then we did a blinded majority rule analysis. So this was actually much more challenging than expected to really pair every colony. I mean, colonies are difficult to distinguish, especially certain species. So we would have to use markers and do and additional images to make sure that every recorded piece of data from one colony was then distinctly matched to a colony later that was digitally analyzed. And we didn't really blindfold the students. It would have been really difficult to get the job done. But what we did was made sure that no one that did a survey in water surveyed that same coral digitally. And we did 3 rounds of digital analysis, and no one did the same coral twice, nor knew what anyone else had scored. And so that's where the blinded nature comes in to ensure we have no bias whatsoever when comparing the 2 methods. And this is my favorite thing to do. How much live coral is in this image? I know no one wants to be the person to say it, but someone's got to say it or it's going to be a painful silence. 1%? 10%? 20%. Anyone want to go larger than 20? 7.5% live coral. So I just do that to show you, like, as an example, you know, we are experts, but we all differ in opinion when we make quick subjective decisions about what's in front of us. So while it's much easier to determine this digitally, it takes more time, and I just want to illustrate from this, while we can zoom way in and see disease, from this flat 2D projection, it's difficult to tell. Whereas in the water, we would expect it to be easier because we can look at a coral from any angle. And if you're wondering why we use the 2D projections, it's because those mosaics and digital elevation models right now are what are primarily being adopted from SFM for characterizing reefs. So we wanted to see if this 2D mosaic could be used to effectively survey coral health. So when we did this, as I said, we matched all the coral colonies. We had 1 in situ observation because we had the 1 dive, but then the 3 blinded majority rule analyses. We had 191 corals that we could successfully, with 100% confidence, pair between the 2 methods. And to start, we had the observers measure coral cover with segments, disease severity, so the actual proportion, but to start, we just compared disease prevalence. That's the simplest way. So did the observer underwater say there was a disease, and did the digital observer say there is a disease? Or did they both say there isn't a disease? And that's what lets us compare sensitivity and specificity. So this table is just showing you when there are both agreement of positive, meaning both methods said there was the disease, or both methods say there are not the disease, and we had bleaching, pigmentation response. What's TIN? It's like the tube worm infestation. Thank you. Yeah, I don't even know what these things are. Macroalgal overgrowth, tissue loss, Parietes trematidiasis, predation, discoloration, skeletal growth anomalies, sedimentation, and damage. All conditions typically surveyed, and then we see, yes, which method, digital or in situ, is better at true positives and true negatives. To do this, we used a Bayesian probability model. So we wanted to do this because with a latent class model, and this was initially developed actually by Hui and Walter in the 80s, when there's no gold standard. So in this case, we don't know what's best. We really don't. So this type of model lets us look at the probability of one predicting that there is or isn't a disease compared to the other. So to construct it as best we could, we used priors from Caldwell, Jamie's paper in 2016. So we're able to, for every condition, give it an idea of what we would expect the prevalence of these diseases to be. And that alters the distribution that the model's using to produce the outcomes, which are based on the data set we collected. So because it's Bayesian, there's no p-values. We're not looking at significant differences. We're looking at the probability that one method gets it correct versus the other. So now I'm talking Bayesian, hierarchical modeling, priors, distributions, no p-values. Maybe you feel like this. So I usually do when I'm working on this. But the nice thing about Bayesian results is they actually tend to be quite a bit easier to digest in the sense that we can ask additional questions and look at several answers as opposed to just, is there a significant difference? So to start, just to show you both majority rule on the top and we did compare it to just taking one single observer. You can see there's a difference in sensitivity from the in situ observations to the digital observations, as well as in specificity between in situ and digital, and it's slightly better and improved in majority rule. That's why I kept them in there to show you that definitely majority rule, using that technique has a good impact on the model. And the takeaway here was just that the in situ approach, so the diver's eyes in the water do have higher sensitivity, But we can now ask, what is that probability? And the answer is about 7%. So a diver is about 7% more likely to properly identify a disease than a digital observer on a computer. But the digital approach had a higher specificity. So it's just a little over a percent less likely to have false negatives. Now, the real moral of the story there is just that both had very high specificity, which is good. We don't want a lot of false negatives. We can then look at each one of these conditions individually using the hierarchical modeling. So working down from damage to bleaching, we can see, and again, the model predicts in situ to always have a higher sensitivity than the digital method. But a few interesting things parsed out where growth anomalies had the largest discrepancy between the two methods, which these are essentially, abnormal growths on the coral tissue. It's a 3D phenomenon, so I think it's just much harder to see in a 2D image, and they often grow on basal regions or sides of coral colonies, so it's just hard to detect. Whereas pigmentation response, which is actually a color issue, was almost similar. So it's much easier to detect digitally because we can color correct that image, and I think color pops out better than sometimes it does in the field where there's a lot of light diffusion. And bleaching overall compared to anything else was the easiest to detect. And I should point out this was done before the current bleaching event, so this is much more patchy bleaching than just overall fully white colonies. If you're curious, these were the actual prevalence values obtained. And so again, the in situ observations typically recorded higher prevalence values, except for, as I said, pigmentation response. But we did also saw the higher discrepancy there with growth anomalies. So I'm just showing this to you because this is nice. It shows that our model predictions are actually very close and what we would expect based on the real data that we pulled out from the two methods. Lastly, this is my favorite result because I've never seen it before. It's always fun to do something new. And so we took that sensitivity difference and mapped it against probability as a function. And so what you're seeing here is that the probability that there's going to be a given sensitivity difference in detecting disease between the two methods. This usually confuses people at first, but I can break it down into this is what I like about the Bayesian approach, sort of a nice way to think about this from a probability standpoint. There's roughly a 50% chance that the diagnostic sensitivity will exceed 8%. So for there to be more than an 8% difference of human eyes detecting a disease over a human on a computer, it's about a 50% chance. But this drops pretty dramatically. So there's only a 33% chance that the human will detect 10% more disease than the same human doing the observations on a computer, and only a 7% chance that the difference would exceed 15%. So there is a difference, clearly, that in situ observations in the field will detect a disease better than a human on a computer, but the difference is not that large, and it's a small probability that it'll be greater than 15%. So to conclude, again, our major takeaway was that yes, the in situ method does have higher sensitivity of detecting prevalence of disease to the digital mosaic-based approach. So this was just using 2D mosaics. But I do think that this also illustrates how useful the digital approach is. To this point, there's only been one study comparing digital to in situ observations of coral disease, and it used frequentist stats, just saying that it's significantly better to do it in the field. But it doesn't let us parse out the performance. And it's nice to really compare performance because we can't always have human eyes on the reef. If we want to go deeper or be down longer or cover larger areas, we need to know what we might be missing. And what I think was really interesting is that neither was perfect. So we're actually likely missing a lot of disease prevalence even when we're in the field using our eyes. If you look at the sensitivities, both are right around 70%. So neither is a gold standard for determining coral health. And I think future research would benefit from continuing to compare this performance rather than just saying, is one method better than the other? And we learned a lot of valuable lessons, like definitely employing blinded majority rule, I think for digital analysis is very important. This can probably be improved by using the 3D models than the 2D mosaic. So as we move to analyzing metrics in true 3D, which Atsuko will talk about, we should also be trying to step away from mosaics and embrace all 3D analyses, because if we were able to look around the whole coral like we do in the field, we might detect more disease. And I just want to state, I think moving forward, it's really key here to identify overlaps where AI enhances the efficiency of this type of data analysis. So we did this, like I said, as an RAU program. This was one component. that we recently submitted to Frontiers. We had a whole nother paper we did from the CS side just focusing on machine learning. And what it really showed us is that the overlap is really crucial. We're often so focused on when can we have it automate everything? When will it take over, do full automated segmentation? And that's at least a few years out. But in the meantime, using convolutional neural networks with bounding boxes, just using this, we found a really good performance of the machine learning to guess where there might be a disease and lead the human observer to then look there. So it dramatically improves efficiency. And the idea is that we not try just use one to simply replace the other, but get to maximal efficiency by working together. So with that, I'd just like to acknowledge there was a number of students that contributed to both these papers that did just a phenomenal job with all the analyses, also the funding. And then just lastly, this was obviously a hard week for everybody. It's really difficult to deal with the loss that we had. And it just got me thinking about the unique community that we work in. It's bizarre. We all come from such different backgrounds. We're all very different people, a lot of us eccentric. And strangely, unlike almost every other person in the human population, we find these topics we're all talking about supremely interesting. If we brought anyone else in here, they probably would leave within 30 seconds. And so we dive into it, and we spend obscene amounts of time in tiny ships in large oceans or in labs, staying up late or on computers, cursing at the screen relentlessly and totally not being freaked out by the person doing that. And it brings us close. In a way, I feel like it makes us like a family. And I think that's why we're our best critics, where we're able to challenge each other and better ourselves as scientists, but we also end up being our best support system. Just like a family, we're there to help each other and be there for each other, and that's, I think, what just makes it so hard to lose one of our own. And, but on that note, I feel so fortunate to be a part of that, and I just encourage anyone, if you haven't, to please visit and share that GoFundMe. I'm sure any support to help would be greatly appreciated. So thank you very much for your time.